Hi everybody, thank you so much. Thank you for coming for network security. This is the third lecture, and today we'll apply the math we have learned in the previous section. So today we're going to talk about symmetric key ciphers. All right. So we'll start talking about Kirchhoff's principle. We'll talk about crypt analysis, and then we'll talk about categories of traditional ciphers. So Kirchhoff's principle says, in simple words, that we don't hide the algorithm, we hide the keys. So whenever we create encryption technique or algorithm, the algorithm we give it to everyone. Everybody knows it. We are not hiding the algorithm. However, what we are hiding? The keys. So the harder to break the keys, the harder to break the encryption, and the more secure the algorithm. So we never try, so the algorithm is known, right? So that's what this Kirchhoff says. So basically when you in the general idea of symmetric key cipher, look careful in here. So in this class we're gonna have Alice and Bob. Alice has a plain text. It could be any message in a plain text that the text we could read, like I love Bridgeport, for example. Okay? It will be encrypted through encryption algorithm with a key. And it will be converted to cipher text. Cipher text is a text that you cannot read, you cannot understand. It's just a bunch of letters that you cannot understand. It will be transmitted over insecure channel. That means anybody could snooping, anybody could traffic analysis, anybody could try to break the key, they can get the data. Okay? When it's received here, you're gonna receive the cipher text. You're gonna pass it through the decryption algorithm, which reverses the encryption algorithm in here using the same key, and then you get your plain text. So Bob, the only way he is able to read the text if only he has two things, which is the algorithm and the key. All right? The algorithm is public. Everybody knows the algorithm. So what remains we have to hide? The key. All right? So that's exactly the symmetric key cipher. Why is it symmetric key? Why do you call it symmetric key? Because there's only one key shared. One key shared, and this key has to be private. So FP for the plain text, and C is for the cipher text, and K for the key. What is encryption? You encrypt using the key, the plain text, you're gonna get the cipher text. What is decryption? Is the reverse process. So D for decrypting using the key for the cipher text, and you'll get the plain text. You'll get the plain text. As simple as that. Can't be any simpler than that, right? Right? So, again, you have a plain text, which is a message, right? Alright? What you have to do, you have to encrypt it. Encryption 4P. Using what? The key. That will give you the cipher. Okay, the recipient will have what? Will receive the C. To be able to read it, he has to do decryption using the key for the cipher. Will give you the plain text. As simple as that. All right. So you do this process with algorithm. The encryption and the decryption, same algorithm. Okay, same algorithm. When you apply the key and the algorithm, you'll get the other side of the story. Either cipher or a plain text. Alright. Alright, so anyways. So encryption algorithm is using the key to lock the data, and decryption algorithm is used to unlock the data at the recipient. Alright. So we go back to Kirchhoff's principle, which I told you. It's a very simple. One more, let's read here. It should always assume that the adversary, Eve, knows the encryption decryption algorithm. We don't hide the encryption decryption algorithm. The resistance of the cipher to attack must be based only on the secrecy of the key. Key is secret. All right. So let's talk a little bit about crypt analysis. What is a crypt analysis? Trying to break the encryption to get the data. All right. So a crypt analysis, it could be divided in the attacks into 4. In this book, they divided in 4. We'll see what they describe them. Ciphertext only, non-plain text, chosen plain text, chosen ciphertext. 4. We'll take examples to explain them. Okay. So again, it's just the definition of this book. You will find other books agree, add more, reduce the number. It doesn't matter. It's just what does it mean? Ciphertext only, non-plain text only. I mean, what does it mean? That means the attacker in this attack knows the ciphertext only. The attacker knows only plain text, one non-plain text. In here, chosen plain text, and in here, chosen ciphertext. Okay, well, chosen, that means the attacker will send the text, wait until it's used, and then try to do something with it. We'll see examples. So, all right. So ciphertext only attack. Ciphertext only attack. We're talking about this in here, right? All right. So ciphertext only attack. We have Alice, our players. Alice sending the message. Bob receiving it, and we have Eve is the evil. Eve try to get the data. So technically, ciphertext will be sent and received by Bob. Both have the keys. She will encrypt. He will decrypt. Everything is fine. So what will happen in here while you're sending the ciphertext? The attacker able to read the ciphertext, the encrypted message. All right. So he analyzes the encrypted message in a certain way and try to get the plain text. It's a very hard process. He does not have the key. He has the algorithm, but he has only the cipher key, and try to get to the plain text. For example, he could apply dictionary attack. What's dictionary attack? Try to find what's your password. What's the password? Are you using your wife name, your son your name, your university, your birthday, your dictionary attack, for example, and it tries to get the data. That's what they call it, ciphertext only. What does it mean ciphertext only? That the attacker has only a sample of a ciphertext. All right. Non-plain text attack. So look in here what will happen. So Alice send the data to Bob. Eve, the evil, read the ciphertext, analyze it, and try to get the plain text. But also, he or she, Eve is she, has a previous pair. Previous pair of what? Of a plain text and ciphertext. Somehow, able to got from before the plain text and the ciphertext for that plain text. All right. So now, is it easier than here or tougher? Easier or tougher?
For the attacker.
For the attacker.
It's easier.
Easier because you have more information, right?
Yeah.
They have more information. That's why we call it non-plain text. Okay. Third, chosen plain text. So what will happen in here? So there is Eve here. So you have a pair created from chosen plain text. Chosen plain text. Eve choose a plain text. Okay. Right. It will send it to Alice. All right. And Alice try to send it to Bob. It will get the plain text, and because the Eve sent both the plain text and try to read also the ciphertext from here. Okay, it try now to analyze it further to find the plain text. So when you have a chosen, when you give somebody something to encrypt and encrypted, you know already the plain text. You don't have to figure out the plain text because you know it. You gave them encrypted, you got the encryption, but now they are communicating for a different message. You could correlate things and try to break the algorithm. So that even will make it more danger. Okay, so Bob or Alice might not know Eve is an evil, right? Could be part from the company or of the network, and it could, you know. And then after that, chosen ciphertext attack in here. So Alice send the data here, all right, and pair created from chosen plain text, okay, and Eve try to read the data and from the chosen plain text, and then analyze it to compare it with the plain text in here, try to build a correlation. All right. So crypt analysis is all about what? Connecting the dots, getting data, getting plain text, encryption, okay, trying to break the key. Once you break the key, you know the algorithm, once you break the key, you're all set. Okay? Okay, so ciphers in general are substitution or transpose ciphers, two kinds. Let's start with substitution ciphers. So substitution cipher replaces one symbol with another. Right. So for example, if you need to send, if you need to...
I have a doubt. Like chosen ciphertext and ciphertext only, aren't they similar? I mean, because ultimately the Eve, he is reading the ciphertext.
Sure.
So
She's trying to read the ciphertext and then try to get the plain text, the real message out of it.
So isn't it similar to the ciphertext only?
The plain text?
No, ciphertext and the chosen ciphertext. I get both. I mean, I am confusing it. Like both are doing the same process. It's just in chosen ciphertext, it is reading the plain text as well.
Sure. I mean, but it's where it's getting from. I mean, also. So in here it's getting it from the recipient, and in here giving it from the sender.
Oh.
Okay. That's all right. So substitution. So for substitution. So for example, if you need to send, for example, Shakur, right? Okay. You don't send you substitute S for X, H for Y, T, O, N, C, for example. Substitution. Substitute. You don't send the message as it is. Okay. The problem is the substitution way or algorithm has to be agreed on between the two sides, right? So substitution cipher replaces one symbol with a node. All right. So so there is something called a monoalphabetic ciphers and polyalphabetic ciphers. Let's take a look at these things, right? So in monoalphabetic substitution, the relationship between a symbol in the plain text to the symbol in the ciphertext is always one-to-one. One-to-one. That means if every X is replaced with Y, for example. It's 1-to-1. Is that good?
No.
It's not good, of course, right?
Because it is easy to get the code what a plain text have. It is easy to get that.
Yes, so it's not good, but that's a basic thing. So examples, for example, in here, plain text hello, okay, it will be replaced with every H replaced with K, every E with H, double L is replaced with double O. So that's a problem. So already this is more information. Again, the crypt analyst trying to collect information. So if you are using this kind of algorithm, then it's known that there is same letter in here, repeated letter here. All right. So the following shows a plain text and its ciphertext. The cipher is not monoalphabetic because each L replaced with different characters. So in here, this is wrong. So it's something else. So they repeated in here. Just check the example 3-2. But in not mono-alphabetic, O, it will not be two O's in here. It will be like different characters. The algorithm will apply different characters there. Okay, the simplest mono-alphabetic cipher is Additive Cipher. Okay, additive cipher. So this cipher is sometimes called shift cipher and sometimes Caesar ciphers. Okay, so how it works, for example, you have the plain text in here. All right, these are the values. Each A is replaced with capital B, B with small b with a capital B. So there is a shift, how much? 26. 26 because the number of digits 26. We start usually with lowercase than the upper case, right? So there is a shift. There is a shift within Z26. Within Z26. So what is Z26? Is the total number of alphabets. Okay, that's the group. Okay, starts from 0 to 25. So, for example, if you'd like to send a plain text, the plain text plus K. K is the shift, mod 26. You have the cipher, you'll be transmitting it. So what's the key in here? Is K. Right? And you're gonna send it. So you receive the C. What you're gonna do is C minus K modulo 26 will give you the plain text. So in here, all what we did in the transmission, we added K, which is the key. All right, and the key should be a number, you know. Anyways, could be any number. And in here we remove it. So that's what we call it additive. The plain text, ciphertext, and the key are integers in Z26. Is this a complex algorithm? No. Because we know that the plain text should be within 26 choices, right?
Yeah.
And we know the key within 26 choices, and the cipher within 26 choices. All right, so it's you could by try and if you write a simple code, trying all the keys, you'll be able to figure it out. Okay. So here use the additive cipher with key 15 to encrypt. So what you do, you have H, which is 07, right? When you encrypt it 07 plus 15 mod 26. And this will give you 22, so it becomes W. So for every H you're gonna send W. For every E you're gonna send T. For every L you're gonna send A. You see, LLAA, which is not good. Repeat it. Alright, simple encryption. Alright? So, for decryption, the reverse process. So in here, we received W, which is 22. All I have to do, minus 15, mod 26 will give you 07, which is H, the reverse process. Right? Alright. So, let's take a look at shift cipher and Caesar ciphers. So historically, additive ciphers are called shift ciphers. Caesar used an additive cipher to communicate with his officers. For this reason, additive ciphers are sometimes referred to as Caesar ciphers. The same thing. So additive ciphers are mentioned referred to Caesar ciphers. All right. So in here, what we have okay, Eve tries keys from 1 to 7. All right. Now it's a crypt analysis work. We're trying to break. All right, but you don't know what's a key. You know it's additive encryption. So all you have to do, trying different keys, right, from 0 to 7. So try. You know how you try it, right? This is the message. This is ciphertext. Okay. You apply it for everyone, and using key, for example, 1. So it's minus 1, okay, whatever it is. So try key 1, did not give a good result. 2, not a good result. Go 7, not very secure, gave you some meaningful information, okay? So this is kind of called a dictionary attack. You know all the possible keys, try them out. Okay? Is it good? Not good. Also, you could do, remember, part of the attack we spoke about snooping and traffic analysis, trying to do statistical analysis. So when you look in here, the frequency, for example. So if you look at the frequency in characters in English, E, the frequency is 12.7%. Okay, T, 9.1. Okay, So if you see, for example, a character that it repeats a lot, most likely it's E, because in English E is repeated the most. You're trying to, I mean, in French will be different, in German will be different, in Hindi will be different, etc., etc. But you're trying to collect all the data. So if you look in here, for example, frequency, not only with the character, with diagrams and trigrams. So in English, these are the most frequent diagrams, and this is are the most frequent trigrams. Of course, the is the most common one. TH in diagrams is the most common one, and so on and so forth, right? So this is statistical analysis. Statistical analysis could help you to do different things. So in here, for example, Eve has intercepted the following ciphertext using a statistical attack. Find the plain text. Here is the data. Okay. So you need to use some statistical attack. So when Eve tabulates the frequency of letters in this cipher, she gets I 14 times, V 13 times, S 12 times, and so on. The most common characters in I with 14 occurrences. This means key equals 4. The key, okay, 4, right? So when she applied the key 4 for that, she gets this message: the house is now for sale for $4 million. It is worth more. Hurry before the seller receives more offers. Okay?
Wait, how did you get that?
What?
That the house is now. How did you decrypt that? The solution, how do you get it?
Well, I mean, what is the most common key in here is E. So E to I, there is 4 difference. Right? So that means we shifted, you know, E to I. Okay, to by it was E shifted by 4, became I. Right?
But there is no letter for a space.
There is what?
A space. There is a space between the words. So how will we come to know, like, if after D there is a space, after house there is space, after if there is
The whole
space?
thing is in one sequence.
Yeah.
Oh, you mean the space in here?
Yeah.
The space is, I think they inserted it just to make it clear for
Okay.
reading and all of that. So it will be consecutive letters, but to be able to read it, I mean, you have to use your English. Yeah. All right. So also you could use multiplicative, right? Multiplicative cipher. So instead of additive, multiplicative. So in here you multiply by a k, but here you have multiply with the inverse, multiplicative inverse. Remember in last class we learned about multiplicative inverses, right? So in here you have multiply by the multiplicative inverse to get the reverse. All right. So in multiplicative cipher, the plain text and ciphertext are integers in Z26. However, the key are integers in the multiplicative inverses, which is less than additive inverses, right? Right? And you know how to calculate the multiplicative inverses from last class. So for example, okay, what is the key domain for any multiplicative inverse? So the key needs to be in Z26. This set has 12 numbers. So these only the numbers in Z26 that have multiplicative inverses. Right? So in the set, not every number in the set have multiplicative inverses, right? So these are the only options for the keys. Okay, same thing. The same thing we did before. So in here we multiply it by 0.7. To reverse it, you have to multiply with the inverse of 0.7. What is the inverse of 0.7?
Minus or something. Minus or something.
What?
Minus.
No? It's not minus. So what is the number? You multiply it by 0.7.
What was it?
Okay, modulo 26 give you 1. That's multiplicative inverse. Try it out. But remember that we are talking about Z26, right? So, for example, 7 times 7 times 8, how much? Hmm?
56.
42?
7
7 times 5, how much? 35.
Sorry.
It will not work. 6. It has to be one of these. So 7, one of these. It has to be, I don't know, I have to calculate it. So one of these will be the multiplicative inverse for the 7. Okay? So in here, what we have to do, multiplicative inverse. So also you could have a fine cipher. A fine cipher, you are using 2 keys. One additive and one multiplicative. So you have a plain text. The first thing you start with the multiplicative. You multiply it with the key 1. Then after that, what you do, you add to it key 2. It will be transmitted. So the first thing you subtract the additive inverse, and then after that you multiply it by the multiplicative inverse. You get. So this will go a little bit more complex. Okay, more complex for encryption. All right. So in here, what you do, you multiply it by the key, and you add the second key for it. Okay, and then you do the reverse in here. So in here, what you did, you minus the additive inverse, and you multiply it by multiplicative inverse. Clear? All right. So manual alphabetic substitution cipher in here. So in here, for example, because additive, multiplicative, and affine ciphers have small key domain, they have small key domain. So for additive has what's the key domain? 26 from 0 to 25. How about the multiplicative? Only maybe 12. Okay, 12, which is all the multiplicative. So a better solution is to create mapping between each plain text character and the corresponding ciphertext. Alice and Bob can agree on these. Okay, so for every A it has to be N, B has to be O, C has to be N. So it's kind of mapping. The only problem with this mapping technique that repeated characters will have repeated cipher, right? Repeated characters will have repeated cipher. So we can use key in figure 312 to encrypt the image. So this message is easy to encrypt. Okay. So for example, T. What is T? Is I. We put I. H. What is H?
C.
C. That's we have C. And good encrypt until all the way. Okay. So the sender and the receiver only has to know the key. Has to only know the key. All right. Is it easy to break it? You could do a lot of statistical analysis until you get the results. All right. So there is now we're gonna go from mono to poly or polyalphabetic cipher. Okay, so in polyalphabetic substitution, each occurrence of a character may have a different substitution. The relationship between a character and a plain text to a character in a cipher is 1 to many. So one character could be encrypted in a different way. All right. So example in here, for example, assume that Alice and Bob agrees to use auto key cipher with initial key value key 112. Key 12. So now Alice wants to send Bob the message, attack is today. Alright, so there is a shift with the 12. So the first key is 12. So in here the plain text. That's the plain text. And this is, you convert it to ASCII. That's the values, right? So A, whatever it is, so on and so forth, right? The first key is a 12. Alright? Right? So A with this key, so you add them, modulo 26 will give you M, 0, 0, plus 12, modulo 26, M, 19. Okay, now what is the key? What is the key for the second letter? It will be the plain text of the previous one. So you see, we started with a 12, the key now became 0, 0 moved here, 19 moved here, 19 moved here, 0, 0 moved here, 0, 2 moved here, 10 moved here, 8 moved here, 18. So we only know the first key. After that, the keys keep changing. It's not the same key. So what they call the key is a derived key. Derived key. Okay, from the plain text. So if you see in here, for example, TT, the first time it was encrypted as T. The second time encrypted as N. Alright? So we have multiple keys, derived keys. So what we call this? Polyalphabetic encryption. Another example in here. So another example in here is like you having the box. One, okay, the box in here. There is rules in here. So you in here what you encrypt two characters together, not one by one, two by two. Okay. So for example, the rules. There's rules says if the two characters in the same line, use the next character. If they're in the same column, use the next character in the column. I'll show you in a second. And they are in different character and column, okay, use the intersection. Okay, so let's say hello, we divide it into 4 syllables. H-E-L-L, okay, you put, to separate them, you put X for example, and L-O. Alright? H-E, where is H? That's H. And E-R, here. So what's the rule says? They are in the same row, take the next characters for each. What is after H? E. What after E? C. Let's take LX. Where is LX? LX. What's after L? Q. What after X? Z. LO. Where is LO? LO. They are not in the same line or same column. So take the intersection. So L, it will be B. You see, L, O, they intersect with B. We put B. Then O. O intersects with L and X. We put X. Rules. Rule. I mean, that's a rule. Who knows this algorithm? Sender and receiver. Okay. Is there a key in here? There is no key. So that's hello the plain text, that's the ciphertext.
Excuse me, sir.
Yes.
In the previous, are we going to always use X anytime we need to fill in for a?
Sure, because you have two. I mean, if you have two consecutive letters, you insert X. That's part of the rule.
Okay, we always use X in particular.
That's the rule.
Oh, okay.
Rule. You could agree with it. I mean, you could insert Y. So the rules in this now, as I told you, and plus if there is two repeated letters, insert X. Okay. Of course, these are all the ciphers, all the techniques we are using in this class. Nobody used them at all. You know that. And this is too simplistic. Nobody used them, right? In here we start just very easy with you to give you the idea how it is. But nobody uses this. Yeah. Okay. So in here, Visionnaire cipher. Okay. Let me remember what's Visionnaire cipher. Yeah. So we can encrypt the message. She is listening using 6 characters keywords. So the key is Pascal. The key is Pascal. So you divide your messages to 6 characters. 6, and the numeric, right? So SHE whatever she is listening, divided. Then you convert it to the plain text values. Here plain text. The key is Pascal P15, A00, L11, and you repeat the key for every 6 characters. right? And then you create the cipher. You add them at modulo 26, and that's the result. That's Visionnaire encryption. So in here in here there is no key. Is there a key in here? Okay. In here we are using a key, but what is the key is 6 character size. It's not 1 character size. It's not additive, it's not multiplicative, right? Right? So usually when the key, so what's the domain for this key? If it's 1 character, the domain will be 26. But if you have 6 character, what's the domain? 6 factorial, right? Much more, right? 6 times 5, right? Much more. So part of the security, increasing the security, we have to increase the domain of the keys. That's why most of the recent cryptography systems, the domain, what's the size of the domain? At least 128 character. If it's not 512 or more, all right? So the longer the key is, the more secure. Why is it more secure? Because the domain of the keys is much bigger, right? So this is in here, the same thing with decryption. So in here you put the keys, so now we move these up and we did the decryption, and it will be done. Visionnaire cipher can be seen as a combination of additive and cipher. So in here, like you divide it into 6 and all of that, okay? And S, H, you distribute them, and you could use the key, which is P, A, S, and you could send them like that. In here, for example, here can say that the additive. So in here, what we have, this is the plain text, okay, and in here the key. Okay, that's the plain text, the key. So if you need to send D, okay, and the key is A, what you have? D. You build it in a matrix. Clear? So here is a plain text, and in here is the key, and in here the corresponding cipher. So let us assume we have intercepted the following ciphertext. This is a ciphertext. Okay. If we do a statistical test for repetition, 3 character segments yields the results shown. So this 3 characters was repeated. First, it happened first at 68. Second time happened at 168. Then the difference 100. This one happened first time at 69, and then 117, the difference 48. Same thing, 68. If you try to take the greatest common divisor for these, you might be able to know the size of the key. You might know the size of the key. So what is the greatest common divisor for these? I'm not sure why I have repeated the cameras. So the greatest common divisor of the differences is 4. That means the size of the key, how much? 4. It's not Pascal. Pascal was 6. 4 now. Try it out, which means that the key length is multiple of 4. So try 4. Okay. You try to decrypt with 4, and that's what you get. You do ciphertext, okay, so you divide it into 4 segments, and you do the encryption, right? Let me go back in here. So what we did in here, okay, the black is the first line, okay, then yellow the second line, and so on and so forth, right? That's what we did. So just you have to organize it in the way it's like 4 segments. So cipher 1, cipher 2, cipher 3, cipher 4, and then try now to decrypt. So what you get? J, U, L, I, then U, S, Julius, okay, then C, A, then E, S, A, R, Caesar. So now you start to read it like this. You got the Julius Caesar used a crypto system in his work, etc., etc. till the end. So crypt analysis is about analyzing, trying to get the key, trying it out. Maybe you get them a good message. Good. Again, these are all technologies. These are here what they are doing now. They're hiding from you what? The algorithm and the key, right? Okay, all the new techniques, the algorithm is known. You're hiding only the key. All right? You have a question?
Yeah, the previous table you showed, is it, no, not this one.
What? This
No,
one?
That,
This one?
yeah. Is it a constant table? Like,
It is a constant table for that key,
oh, okay.
using that key, chosen key. Okay?
So basically, every time I would send you a message, we make our own key.
Our key, then you build the table, then you encrypt the crypt using that. Okay? Which is very primitive again. I mean, we don't do that nowadays, right? All right. So in here we need to, you understand from the concept, from the basic, what is substitution, what is transposition, how it happens and all FUCA. Then after that, as we grow, you'll see this. This is for learning, you know, okay? For learning and for understanding. It's very hard to jump from to the current dictionary, right? You have to grow, right? Another technique in here, like you divide the data into matrix, right? So key in here, okay? So the key matrix in the Hell Cipher needs to have a multiplicative inverse. So the key, you build the key, a matrix, but one condition, it has to have a multiplicative inverse. And which matrices have multiplicative inverse? It has to be a square matrix, right? So we create a okay, here's the condition. A square matrix that has multiplicative inverse. Simple, all right? And then you try to build the data. Maybe there's an example in here. So for example, so you have a plain text, you multiply it with your, and we spoke about matrices last time, multiplication, right? And multiplicative inverses, right? So in here, you multiply to get the cipher. If I need to get the plain text, what you have to multiply it with? The multiplicative inverse matrix. So what is the key now? The key is not a digit. It's not a group of digits. It's what? Matrix. A square matrix. Condition, it should have multiplicative inverse. Okay? Same thing in here. So assume that Eve shows that M3 she has anticipated 3, whatever. I mean, so that's the plain text. So transmission. So that's the plain text. That's the ciphertext. You could build a matrix like this. Okay, that's where is the danger. So now what you know now? You know the plain text and what you know? The ciphertext. You know the plain text. You know ciphertext. Can you get the key? That's where's the danger, right? So very simple. So you have the ciphertext, calculate the inverse matrix for the plain text, multiply together, what you get? The key. You're done. The key is gone, right? So that will become a danger. If somebody catches a ciphertext by itself, it's no use. But if he can get cipher with a text, okay, that's danger by itself because your message is read already. It's disclosed, right? But the worst thing, if that happens, you could also manage to get the key. And once you manage to get the key, what you get? Everything after that, right? So sometimes we have one time bad. Okay, another technique is like a rotor cipher. So this, for example, initial for every character. So it's set up like in a certain way. So after the first transmission, it rotates. So it will change. After 26 rotations, this will rotate once. And after 26 rotations of this will rotate once. Okay? So for sending the first 3 characters, okay, the first time 3 characters, let's say that you are sending A. Okay? So let's say that you are sending A. So the first A will be sent as E. The second A as A. And the third A as E. Okay. The second time, let's say we're gonna send the same thing the second time. So this will change, only the first one will change. It changed to different rules, right? But the second 2s will stay. It will change only once every 26 times. After 26, right? So this is another cipher also, okay? Again, the sender and receiver have to agree in a transmission. Also, you could have in here the shaft or schematic, where you have like first rotor, middle rotor, okay, system, enigma, machine, and certain rules could do that. This all we spoke about was what we call it, substitution cipher. We substitute something and something else. Now what we are using in here, transposition ciphers. All the recent encryption techniques use both substitution and transposition. All right. So I'm sure that you understand now what is substitution. It can poly, it could be mono alphabetic or polyalphabetic. Right. You understand these terms very well. Right. With many examples. You're given so many examples to understand them. Moving on. So a transposition cipher reorders symbols. So we don't substitute, we reorder. So A, if we transmit A, will stay A, but it's some location, different location, right? So for example, one example for a transmission, if I need to send, for example, a message, what is the message? Meet me at the park. So what I do, I make like a matrices. Meet me at, so I don't send, I send MEMATEAK, and then I send ETETHPR. That would be the message transmitted. Same characters, but they are reordered according to a certain agreement. All right? And here, for example, you could put it like this: meet me at the park. So I don't send it like this, I send it like that. MMTAEEA, and so to the end. Right? So in here what we did? Transposition. We changed the location only. We did not substitute. Okay? So example in here, the cipher in example is actually a transmission cipher. The following shows the permutation of each character in the plain text into the ciphertext based on the positions. Okay, based on the positions. So the first location, move to the first location. Of course, right? M always move to the M, right? Like this, or this will be move to the M, right? Right? Because the first location, you're gonna come in here first, right? Then after that, number 2 move to 6, number 3 move to 9, number 4 move to 13, and so on and so forth. Okay? Number 15 move to 12. So if you go back in here, number 15, where is the number 15 in here? The P, okay? What is it? What was the message again? K. K moved to where? To 12. It's true in 12. Right? Move to 12. Supposed to be here, move to 12. Right? Anyways. So that's what is a transposition. So Alice needs to send a message. Enemy attacks tonight to Bob. So enemy attacks on tonight. And added Z to make it like 1, 2, 3, 4, 5, 6, 6. So in the transposition, the first character will go to 2. Okay. So what's the first in here? The third goes to 1. Where's the third? E. Okay, move to where? To 1. We have E. Okay, the first moved where? To second. What is the first? key, move to the second, and so on and so forth. Okay, so in encryption, we do this, and in decryption, we do that. That's what we call a transposition box. We're building a transposition box. Okay? It could be much more complex. So, for example, combining the two approaches, you have the plain text in here, you divide it in a matrix, okay, and then it's not what you are switching, not the characters, but the matrix column. So this column will move to here, this column will move to here, and so on and so forth, right? And you're sending the columns. When it comes in here, you're switching the columns back. So this box, this key box, is to switching what? The columns location. The columns location. Alright? Alright, so this is in here, the box. This is encryption, key, and this is the box, and that's a decryption. So you could go through this again, it's the same thing. I don't want to, And here, for example, in here you have the plain text, that's encryption key, and the cipher key, when you multiply them with the cipher key. So we can use matrices to show the encryption decryption process Substitution Cipher. Okay, using the, so in here what will happen, that every line has only one. Has one, and every column has only one. Okay. Anyways, you could take a look at that. You could have double transposition ciphers, and that's what we'll use in the recent. It's not one, it's like for 16 consecutive transpositions. It's like you have a blender, you put banana, then you put orange, and then you put apple, then you put whatever, strawberry, and you operate the blender. You blend all the data together. Then after that, until you give me banana. Can you give banana? So when you do it 16 times transposition consecutively, I mean it will be. So in here, for example, you write row by row, then you permute the columns, then read the columns by column, and so you do multiple operations, as you will see in the real encryption later things. So it's like you're mixing them, you do different things. However, you have to know what you did, because when you go back, you have to apply them what? In reverse. Okay? You have to apply it in reverse until you get to the result. So you started with write row by row, and here write column by column. Permeate columns, then here, and so on and so forth, until you get to the end. Alright, so now there is two kind of ciphers. So there's stream ciphers and there is block cipher. What's a stream? That as you use streaming, you're encrypting. So you encrypt character after character. But a block, what you do, you divide your data into blocks, and you encrypt the block, you send it. The second block, you send it. Third block, you send it, and so on and so forth. So the literature divides the symmetric cipher into two broad categories: stream ciphers and block ciphers. Although the definitions are normally applied to modern ciphers, the categorization also applies to traditional ciphers. So let's start with stream ciphers. So in stream ciphers, for example, you have a plain data, and you encrypt. So the first character with K1, K2, K3, K4. So every character could have different key for encryption until you do the transmission. So that's the plain text, that's the ciphertext, that the keys. All right. So the first P1 is encrypted with K1 to give you C1. P2 encrypted with K2 to give C2, and so on and so forth. That's a stream cipher. Okay. So as an example, additive ciphers can be categorized as stream ciphers in which the key stream is the repeated value of the key. In other words, the key stream is considered as predetermined stream of keys. So the key is the same thing. Remember, in the additive we use 5, so it's the same key all the time, right? Anyways, another example, you could take a look at it. You could take a look at that. So see anything in here. Okay, the block cipher. Okay, I'm sorry. So the block cipher, a group of plain text, or so this should be, I think, block. The title is wrong. Should be block. So in here, the plain text is divided into blocks, and then what you do, you encrypt the first block, the second block, the third block, and you send that. Okay, but using the same key. Okay, it's like you divide the data into blocks. So if you need to encrypt a hard disk drive, you could use a block. Why? Because hard disk drive built of blocks of data. You divide into blocks, encrypt it, and save it encrypted. But if you are, for example, streaming a video, or streaming a voice, or streaming a data, you don't know the rest of the data. So what you need to do as you transmit to do the encryption, right? So that is the difference. So you could have many, and you could have combination. Most of the recent, as we'll see when you study this, 3 triple this, all of these, they have combination of 2. And it's very complex that it's repeated like 16 rounds and so on and so forth, that the data will be completely mixed. Mixed is very hard, unless you know the rules, it's very hard to get it. Alright, so what we have learned in this class, we learned about the traditional symmetric key, where we have to use key. Okay, we learned at the beginning about crypt analysis. What are crypt analysis? What the job of a crypt analyst is to try to break the encryption. Then we said that there is 2 general techniques for encryption. One is substitution. The second one is transposition. Right? All right, and that's in a mechanism. In terms of the data, there is a block and there is a stream. Cipher or encryption or cipher, okay, and the most recent use all the 4. All the 4 will be used, as we will see that. We gave you many examples for substitution, cipherment, and we gave you many examples for transposition. What we covered in here these are simple techniques that not used in the recent, encryption, but they gave you idea of the concept, and that's all. Next class, we're going to have another mathematical session, and then after that we'll start. Okay, as you see, this book or this text or this is like it's moving you nicely, smoothly from one area to area, and it's very clear today. If you did not study what we learned last class about the sets Z, about multiplicative inverse, about additive inverse, many things will be like not clear for you to understand here. Same thing as we'll go. So please try your best when you go home, spend 2 hours, go over the slides, understand it, go the homework, wait for the next lecture, and so on and so forth. You'll be okay. All right? Thank you so much.